Hello, in this video, we're taking a look at another example of finding the Taylor series for a function and then finding the interval of convergence for that power or Taylor series. So we want to find the Taylor series for sine of x centered at a equals pi over 2. So since it's a Taylor series, we have a center that isn't 0. So we're looking for a series of the form. We have the derivatives of our function at pi over 2 all over n factorial times x minus pi over 2 to the n. We need to find those derivatives, so let's take a look at what are the derivatives of sine at pi over 2. So n, our original function is sine of x. And we want to plug in pi over 2 to that. So sine of pi over 2 is 1. When we take the first derivative of sine, that is cosine. And cosine of pi over 2 is 0. Second derivative of sine is the derivative of cosine, so that's negative sine. And the second derivative of sine at pi over 2, meaning negative sine of pi over 2, is negative 1. Third derivative is negative cosine, which at pi over 2, that is 0. Fourth derivative, we're back to sine. And sine of pi over 2 is 1. So writing out a few of these terms, we have 1 over 0 factorial x minus pi over 2 to the 0 plus 0 over 1 factorial x minus pi over 2 to the first plus negative 1 over 2 factorial x minus pi over 2 squared plus 0 over 3 factorial x minus pi over 2 to the third plus 1 over 4 factorial x minus pi over 2 to the fourth. And this continues on. That pattern keeps repeating. However, every other term, specifically every odd term, is going to be 0. So this is 0. This is 0 because those derivatives are 0. So this simplifies down to 1 over 0 factorial x minus pi over 2 to the 0 plus negative 1 over 2 factorial x minus pi over 2 squared plus 1 over 4 factorial x minus pi over 2 to the fourth. Now I can actually add on another one knowing the pattern. It's going to be negative 1 over 6 factorial x minus pi over 2 to the sixth, and so on. We're getting these even terms where all of the exponents are even and all of the factorials are the even factorials. I would really like to be able to write a series that only picks out those even parts. Well, a really easy way to only get even numbers is instead of saying n, we have 2n. So if I have n equals 0 to infinity, I could divide by 2n factorial. And so when n is 0, that would be 0 factorial. When n is 1, that would be 2 factorial. N is 2, 4 factorial, and so on. And the same thing would apply for the exponents. I could get those even exponents by making the exponent be 2n. I could do odd exponents when I have 2n plus 1. And then the last thing, so we'd have all the factorials, we have all those exponents appropriately. The last thing is just, how do I get these numerators? What the numerators are doing is they're alternating. That's a -1 to something piece. So that is a -1 to, it's either going to be n or n plus 1. You want to figure out which one that is. Well, if I plug in 0, I want a +1. So I want -1 to an even number. 0 is even, so this should be n. When I plug in 1, I'd have -1 to the first. Perfect. -1 to the first is -1. N equals 2, -1 squared is 1. So this has broken this down into an n equals 0, n equals 1, n equals 2, n equals 3, and we've cut out all those odd terms we had before where everything was 0. So there is our power series for sine. And then the second part of the question says find the interval of convergence. Finding the interval of convergence is running that ratio test. So the limit as n goes to infinity of -1 to the n plus 1 over times x minus pi over 2 to the 2n over 2n plus 1 in parentheses, factorial, all divided by -1 to the n x. It should be 2n plus 1 up here. X minus pi over 2 to the 2n over 2n factorial. Keep, change, flip. This is the limit as n goes to infinity. I'm going to drop the -1s because they're inside an absolute value. They're not doing anything. We have x minus pi over 2 to the 2n plus 2 times 2n factorial over 2n plus 2 factorial times x minus pi over 2 to the 2n. This simplifies down using the rules of factorials and the rules of exponents into x minus pi over 2 squared over 2n plus 2 times 2n plus 1. That numerator is fixed. X is representing just a number, any number at all. Whereas the denominator is growing to infinity, so this limit is 0. Just like in the e to the x case, 0 is less than 1. So by the ratio test, the series n equals 0 to infinity, -1 to the n over 2n factorial times x minus pi over 2 to the 2n converges for all x, making the interval of convergence -infinity to infinity. So the Taylor series for sine, centered at pi over 2, converges for all x. There is our second example of finding a Taylor series.